All right, one last time. Checking out a little calculus 7-6 solids of revolution instead of 19D. Solids of revolution sounds like a great band name, but the idea is that you take an integral that you know and love. This is an area under the curve, and you spin it about the x-axis or whatever axis you like. I guess it would look like this, and then come around this side like that. And as you do that, this makes spins, and it makes a solid here. And the idea is that we want to calculate the volume of that solid using some calculus. There's a lot of ways to do it, but there's some interesting calc applications. Why would you want to do that? Well, anytime we are dealing with a volume that isn't a nice geometrical triangle or something to that effect, you need to find the area. It's easy to find a mathematical model that talks about this little curve, right? And then you can integrate under the curve, you find the two-dimensional area, and then you perform this fancy solids of revolution trick, and it gives you the three-dimensional volume. Ching. And that works well when you have any sort of rounded edges. You can kind of section them off and do this. Housings and submersibles and anything with volume, you can play this game with. And it's not that big of a trick. Here's the idea. One way to think about volume of a cylinder might be taking flat discs like that. Here's your disc, and then taking the base and just multiplying by the number, like stacking up washers, right? So then if you stack them that way, this is where they get the volume is the area of the base, right? It's this times the height times the number of washers you have, right? That's one way to look at it. Another way to look at it is like this, and it's not exactly geometrically correct, but this is kind of how I visualize it. You can think about having this area instead of the area of the base, and then having those fan out like that. Now it's coming out towards you. It's coming out towards you even more, like that, right? And now it's aiming down. And if you had enough of those packed in there, you'd have a three-dimensional thing with a volume. So I kind of think about this as another way to think about this is like volume is the area of the cross-section, maybe. And then we kind of have to multiply by, we have to have another piece of it, and then we have to have pi to talk about a circle going around. So there's like, I'm going to just put in here a multiplier to make it 3D, and then a pi component. So let me show you that here, just what we're doing. So this is our curve, 0.1x squared, and this is the area underneath it. Move my face out of the way. Get your face out of the way. Still here. If we grab that, and then what you can do is I'm going to move it around so it has a little bit more dimension, but I'm going to start doing this to it. You can't really see what's happening to it yet, but if we change our alpha, it swings this out. Whoa, too much alpha, too much alpha! We move our alpha a little bit. You can see this is the idea is that you take that volume and you rotate it till it comes all the way back around, links up with itself, and now you've got a three-dimensional surface. Yeah, and it doesn't really matter what equation you use for this. You can just use x, right? Oh, y equals, yeah, let's just use x. There's x. We still have these ends going on. So our area under the curve is still there. I'm going to put that out to 5. And if we turn this alpha back on, spins us. There's our cone. It's not the greatest view, but that's all right. Neither am I. But you can see how that would work, that our area is just rotating under the curve, going all the way around. Okay? And you can do that with all sorts of interesting equations, and I'll show you another one in a sec. But that's the idea. So let's try to figure out how to do that mathematically. Get my face back in there. Let's go. Okay. You get the idea. Here's some 2D images and how they become three-dimensional when you look at them. It's really easy to describe the curves often, and then they helpfully give you the volume if you do the math right. So here's how to do the math. The volume, when you want to find the revolved volume, you take the curve that you want. If it's a definite integral, it should be a definite integral because this is an actual tangible thing that we're holding on to. You find the area under that curve. Right? That's the idea, is that you're finding the area and then revolving it. And you revolve it like this. You square your equation, right? So this curve, I don't know, might be negative cosine. This would be y equals negative cosine x plus 3, making stuff up, right? You would take that, you'd take the whole thing, negative cosine x plus 3, you'd put it in there and you'd square it. You would then integrate from whatever limits you want, and then lastly you'd multiply by pi because it's going around in a circle. You need to square it because it's going from one dimension to two dimensions, right? Just like if you squared a side, if you said a squared is not a one-dimensional thing anymore, it's two dimensions. So once this squared, it tells you that it's coming out towards you. Pi means it's rotating circularly. So let's try a problem like that. We're trying to make a cone. I know the line that we're trying to use is y equals x, and I know it's going from 1 to 4. It's 1 to 4. So let's find the volume. First we're going to do it with fancy calculus, and then we're going to verify it with lame old geometry. So here's our equation for the volume of revolution. This means I'm going to take whatever line I have and square it, whatever equation. It happens to be x, so I'm just going to put x in there, right? So that's what this looks like, and we're going from 1 to 4. I don't want the tip of the cone for some reason. Maybe it's like one of those shouty "Go Team Go" cones. All right, integrate, no problem, right? This x squared becomes x cubed over 3, and then we substitute in 4 and 1 into there and subtract, right? We evaluate. So when the 4 goes in there, you get 64 over 3. When the 1 goes in, you get 1 over 3. Leave pi. Everybody loves pi. Leave it alone, right? Don't multiply it in there. Nah, this is exact. And there you go, 21 pi cubic units. You can do the same with the lame old geometry method, 1/3 pi r squared h. Essentially this means it's the same volume as if this were a cylinder, but it's a third of the size. It's a third of the volume. Yeah, you could pour 3 of these cones into this cylinder of the same size. That's where it comes from. There's a cool physical proof about how to do that. So in this example, our height is going from 4 to 1. Oh, we're going to have to do this. We can't play that game. Can't play that game. We have to find the volume of the big cone and then subtract the volume of the tiny cone on top, right? So the volume of the big cone would be, I'm going to move that over there. Volume of the big cone is from 4 to 0, so 4, that's the height. The r is the same for all of these. Let's see, at 4, this will be 4 and 4, right? We put in 4 for the x, and 4 comes out for the y. So the radius for the red cone is 4, right? So r equals 4. Radius of the small cone is going to be 1. R equals 1. And then the heights are there too, 4 and 1. There's that piece, and then as you crush that, wow, guess what? 21 pi. Neat. Okay, let's try it another one. Fancier equation. Here's our equation. We want to find the volume when it's rotated through 2 pi. It means all the way around. If they're tricky, they'll tell you only pi. You find the whole thing and you divide by 2. Or if they tell you, oh, it's really pi halves, find the whole thing, divide by 4, right? Take whatever chunk you want. You're just taking area. So This is going all the way around. That's nicey nice. So plug in what we know. Y is going to be x squared. The whole thing's going in there. And we're going from 0 to 5, sorry. So x squared squared, dx. Great, there's that. And then integrate. So x to the 5th over 5, not a problem from 0 to 5. So plug in 5, plug in 0. The 0 doesn't really matter. And then pi is still there. Don't multiply it in. You kidding me? Great. So you can also do this with your calculator, your graphical display calculator. You down with GDC? Yeah, you know me. Who's down with GDC? All the homies. If you plug into your fancy calculator, x squared, no, x to the 4th. We're plugging in this piece, x to the 4th. And you just get to a graph. Zip. I zoomed in on this so we can see it better. If you say, please calculate for me the integral from 0 to, what was it, 5, bam, it says, all right, here's 625. It did all this work for me. It did this piece, and all we have to do is tack on pi. Multiply by pi, bam, there, done. And that's it. So you can use your trickery with the calculator if you're allowed on the test. Go. All right. Let's try one more problem, and then I'll show you a little trick. So they're not going to let you get away that easy. There's some mathematical treachery that you might see. They said an arch, here it is, rotated through 360, goes all the way around. That's good. Using this identity, right? So they're giving you this sine squared is really this piece. Help you find the volume. Okay, well, this is sine of x, so if we threw that in there, you'd get sine of x squared, right? Sine of x squared is sine squared of x, and then instead of this, they plugged in this. So it looked like that. And that's easier to integrate. Sorry, so this integrates to this piece, this half stays in front, and then we undo the chain rule. We integrate by U substitution to get this piece, and then plug in your pi and your 0. Right? Great. So same sort of thing, but sometimes they'll throw a little wrench in the works to go from here to here because we don't necessarily know how to integrate that. Right? All right. Last little bit is that sometimes they can give you not the area between the curve and the x-axis, but sometimes they'll make a hole like a donut and only ask you for this part, like that. They'll say, here's one curve, here's the other curve. We're putting the two ideas together, the area between the curves. Please integrate that. Well, it's the same sort of thing. You find the area under here. You find the area under here. You subtract, and you're left with only this piece. Right? That's this. Square them both, subtract, and then revolve it. Right? So it would give you this donut shape. If you were looking at this guy, here's two curves, and they don't touch the ground, and so I might just move this out a little bit to show you the visual of this. It's a little clunky, but that's all right. All right. So it would look like this guy. As you go around, it's not quite hitting the x-axis. So you're just doing a little subtraction, right? It's kind of cool. All right, let's jump back. So let's try one here. So we want to find the volume of this rotated around the x-axis, all the way around. Okay, well, we can find the top curve, find the area under that from 0 to 1, find the bottom curve, find the area under that from 0 to 1, and subtract, and you get this interior component. Yeah, we need to square them both first. So let's try it out though. So upper curve is going to be this guy. So that's where this comes from, right? We're squaring it first. Lower curve is going to be this x squared, squaring that, and then subtracting them and integrating between 0 and 1. Right? So this is nice. This is nice. As we integrate, you get this and this, and then you plug in 1 and 0 into that whole thing. This is with the 1 in there, and this is with the 0 in there, which is nice. And so 3/10 pi units. And the figure would look like that. Ooh, three-dimensional. All right, that's it. That's all the math that you can have for your high school career, or else you'll become too powerful and can take over the world. So you're going to have to go to university and get the rest of it there. Nice work. Thanks.